Okay, so in chapter 6, we'll see how to apply the concept of entropy. To start with, in the previous chapter, we have already seen the second law of thermodynamics and how we have energy entropy production and what is the difference between if you want a reversible and irreversible case. In this chapter, we'll focus more on introducing theorems that can help us into evaluating this as numbers. And this is why we'll introduce a new variable, which is entropy. So in this chapter, we'll explain the key concepts related to entropy and the second law, including the entropy transfer, entropy production, and the increase in entropy principle. Plus, we'll evaluate entropy change between two states and do analysis of isentropic processes. Whenever we say isentropic processes, this means that S is constant. Now, we'll apply, if you want, isentropic efficiencies for different types of equipment like turbines, nozzles, compressors, and pumps, as we did in previous chapters. So if you want, this chapter will be a little bit similar in concept, how to use the tables, how for each state to determine the entropy. And then once we determine the entropy change from the table, we can apply the second law of thermodynamics on each of the components. Okay, first, why we introduced entropy? We have seen before, okay, that the first law of thermodynamics will allow us to see how heat and work can be transferred in a certain system, but we cannot predict if a process can happen or not. To be able to know if a process can happen or not, we use the second law of thermodynamics. And in chapter 5, we have studied two ways, if you remember, the efficiency, okay, and we did the Clausius inequality to determine if a process can take place or not. And now in this chapter, we'll continue this. This chapter is a continuation of this to understand more the Clausius inequality. We'll introduce what we call the entropy. Now, let us try to link entropy to the Clausius inequality. We have seen in previous chapter that if I have a cycle, and whenever you see this symbol, this means that you are doing the integral over the cycle. If you integrate over the cycle, del Q over T on the boundary of your system, you obtain a certain number. Okay, and we have seen in previous chapter that it is impossible to get this integral positive. This means that sigma can never be negative because the integral is equal to minus sigma. Okay, so sigma cycle will always be positive. And in this chapter, we'll do the interpretation of this sigma. This sigma represents what? So in case you get for your whole cycle, integral over the cycle, del Q over T at the boundary equals to 0, then you can say that you have no irreversibilities within your system. If you get sigma positive, this means that you have irreversibility within your system. And if you get a negative result, you say it's impossible to have this cycle. So this is why we say that the second law of thermodynamics can help us to know if a process is possible or not. Because if they gave us numbers and we want to judge if it's possible to have the cycle or not, we can calculate integral over the cycle of del Q over T. If we get a negative result, we say this cycle cannot take place. Please stop me if you have any question, okay? Now, how to use numbers, okay, or a variable that can help us to quantify this. We thought about going from one point to the other. So let's say I have 2 points, 1 and 2, okay? If I go from point 1 to 2, I have several possibilities to go from 1 to 2. I can go through scheme A, through scheme B, through scheme C. And then if I want to go back to A, I can go back also with any scheme, with any pass. Okay. In case I have no reversibilities in my system, when I go back to the same point, I should not lose, if you want, energy, and I should not have entropy production. Now we said if a cycle is reversible, I should not have production of entropy. This means if I go to 2, then go back to 1, okay, since I am going back to the same point, then I am doing a complete cycle. I should have integral of Q over T, integral Q over T for the whole scheme, and of going back and forth, should be equal to 0 to say that my processes are reversible. Okay, so from here we said, let us try to define a property related to this. So as I said, let us consider point 1. Okay, I can go from 1 to 2 in pass A, then go back from 2 to 1 using pass C. Or another possibility, let me go first from 1 to 2 through B, then come back through C. Okay, if I say that my processes are reversible, what can I write? I can write that del Q over T over pass A plus integral from 2 to 1 del Q over T for pass C is equal to 0, because I consider that I have reversible processes. And I can say the same thing when I go first into pass B, then into pass C. Okay, if I look at my equation, this means what? This term is the same. Okay, so to have a completely reversible cycle, what is the condition? The condition is that integral from 1 to 2 of del Q over T in pass A should be equal to integral from 1 to 2 to del Q over T over pass B. And this means that whatever is the pass, because I selected A and B randomly, any pass between 1 and 2, okay, should give me this result if it is reversible. So from here we can conclude that if a process is reversible, then integral del Q over T from 1 to 2 should be independent of the path of motion. So this is why we said that from here we can define a certain state variable, which is the entropy. Why? Because if you remember how we define let's say internal energy, enthalpy, etc., we said that this variable will only depend on the state. And if I am at point 1, I can directly say I have one possible value, which is S1. And if I go to point 2, at point 2, I have S2. I don't care for the path of motion from 1 to 2. This is the same for enthalpy, internal energy. It's just depending on the point. Okay, because the value of this integral is independent of the path, okay, and will depend only on the end states, from here I can define a new variable, and this variable is the entropy S. Okay, so for this reason we said let us define the entropy in this way. If I go from point 1 to 2 in a reversible way, I can say that S2 minus S1 is equal to integral from 1 to 2 of del Q over T. Okay, now what will happen if I have irreversibilities? We'll see how we modify this theorem to account for irreversibilities. But please keep in mind that delta S will represent always the entropy change. If you have reversible or irreversible process, you can say when I go from 1 to 2, I can determine the state at point 1 is S1 and the state at point 2 is S2. So the change in entropy will always be equal to delta S. But if it's reversible process, delta S is equal to integral Q over T. If it's irreversible, then I should add the entropy production, and we'll see this in future slides.
دكتور عندي سؤال.
Yes.
كيف بعرف إذا البروسيس هو reversible أو لا؟
Great. نحن هلا حنتعلم بهيدا الشابتر كيف نعرف إذا البروسيس is reversible؟ ليه؟ لأنه أنت you are able first. Okay, let us say I gave you, for example, 2 points, 1 and 2. Okay. If you go to the table, you can get S1 and you can get S2. Okay. So you can evaluate what? You can evaluate delta S. On the other side, also, I should give you information to be able to evaluate integral from 1 to 2 of Q of del Q over T. Okay. If you get the same result, this means that your flow is your process is reversible because you got the same value. Okay. However, if you get different values, so if delta S is different than integral from 1 to 2 of dq over t, this means that we should add here, okay, we should add here a certain term. Hey, that term هو اللي بنسميه entropy production اللي هو related لسيجما. And now we'll see this after in the coming slides. Okay. يعني أنت you can evaluate this and this. If they are equal, your process is reversible. If they are different, this means that you should add a term which is related to the entropy production. Okay. And the entropy production is always positive. It can never be negative. Okay. اللي هي السيجما. هلا we'll talk about this together. Okay. And we'll take examples to see how we determine if it's reversible or not. So just keep in mind that in case it's reversible, delta S is equal to from 1 to 2 is equal to integral from 1 to 2 of del Q over T. If it's different, this means that the process is irreversible. Now, how to find entropy values? For entropy values, it's very similar to internal energy, to enthalpy, etc. You use tables, and now you know well how to use tables. For each, they can give you, for example, pressure and temperature. You should know in which state you are to use the specific tables. So the use of tables is very similar to what we did before. So as you find UH, you do the same to find S. If you have, for example, a mixture, then what should you do? You should go to find the quality, and then you can write that S at a certain point is equal to 1 minus X SF plus X SG, or it's equal to SF plus X SFG, which is SG minus SF. And in case also you have a compressed liquid state and you don't have the corresponding tables, you can do the approximations that S of at TP can be approximated by S at point F at the same temperature. Please pay attention, at the same temperature and not at the same pressure. Okay, now, concerning graphs, also here, if you remember, in general, we, in the majority of cases before, we draw P function of B. Now, in this chapters, we'll start to draw also T function of S, because we'll see that T function of S will be helpful into solving our problems. And keep in mind, okay, that for closed system, we know that omega is integral PdV for closed system. Okay. And we'll see also here when we continue that we can evaluate a Q as integral TdS. We'll see how. Okay. This is why the graph of T function of S will be helpful for us in order to do the analysis of cycles. So let us first try to define equations that will be helpful and for us to evaluate a graph T function of S. You should know the following relations. Okay, you have that TdS can be computed in two different ways, and which way to select depends on what we have. I will discuss this with you now. And for example, if you say TdS is equal to du plus pdv, if you have, for example, constant volume, what will happen? dv will cancel out, then TdS will be equal to du. While if you have an application of constant pressure, which equation you use? The second one. And how you can go from one equation to the other? It's very simple, because you know what is the relation between U and H? You know that H is equal to U plus PV. Okay, so DH is equal to DU plus PDV plus VDP. Okay, and then if you just replace DH, okay, by its function of du, and here you can say instead of du I will replace du by dh minus PDV minus VDP. If you do this and you put instead of du dh minus PDV minus VDP, this term will cancel out. Minus PDV plus PDV, you will just have dh minus VDP. So these two relations both are right, and which one to use depend on the configuration. When I have constant volume, this term will drop, I will use this. When I have constant pressure, this term will drop, then I will use this. Okay, and we'll see together how to apply these formulas in the coming slides. So first, okay, we said that from previous equations, if we have constant pressure, whenever you have, for example, a process here between, if you have a process on a line of constant pressure, you can directly say, let me use the second equation. So for P constant, we can use directly that dH, so the variation of H is equal to dds. Okay, this is why you can see from tables, if you take points F and G, okay, you have that delta S, so SG minus SF will be equal to HG minus HF over T. Why? Because between these 2 points, T is constant. Okay, when you are inside the dome and you have change of phase, T is constant. So you can say, since T is constant, I can write delta H is equal to T. Please pay attention, only inside the dome. لأنه نحن إذا عندنا constant pressure inside the dome, T is constant, but outside you have variation of temperature. So inside the dome, you can write that delta H is equal to T, which is constant, times delta S. This is why G minus SF is equal to HG minus HF over T.
يعني دكتور إذا ما بعرف كيف اكتشفنا إنه فتنا على التيبل ولقينا إنه هي mixture دغري فينا نستعمل DS equal DH over T.
إذا عم نروح from 2 points بقلب الدوم، yes. إذا أنت عم تروحي من point هون لpoint هون، أوكي، في عندك طريقتين تجيبي دلتا S، أو بتجيبي S at this point و S at this point وبتعملي دلتا S، فيك تجيبيهم من التيبل اثنيناتهم، أو فيك تقولي إنه فيني أعمل كمان H2 minus H1 over this temperature. You can verify إنه بيطلع لك نفس الشيء. بينما إذا عندك point هون و point هون you should do delta S، لأنه ما فيك تكتبي delta H over T لأنه T هون it's varying. أوكي؟
دكتور طب للبوينتس نحن بنعرف من ورا الكواليتي؟
أكيد مثل
يعني
العادة.
أنت بتعطينا إياها.
أكيد مثل العادة، أنتم بالجيفن بتحددوا وين البوينت لإلكم، إذا saturated vapor، إذا saturated liquid، إذا أعطوني الكواليتي يعني mixture، إذا عندي إذا طلعت بالبريشر والتمبريتشر وطلع عندي superheated أو compressed، هول كلهم مثل قبل. You can find them exactly the same way. Okay.
دكتور هاي الفورمولا بس على saturated vapor و saturated liquid أو
لا، هي بتزبط بحيلا 2
الدوم
points، حيلا 2 points بقلب الدوم على constant pressure. لأنه بس تكون constant pressure بقلب الدوم كمان شو بتكون T constant، بس in particular كمان بتزبط من F ل G. it can work also from F to G لأنه هول البوينتس بقلب الدوم يعني P constant and T constant. Okay. Okay, let us continue. So then let us now use, if you want, particular cases for to find the variation of entropy. خلينا نرجع للcase of إذا عندي incompressible substance. Okay. شو يعني أول شيء incompressible substance؟ حتشوفوا إنه كل الفورمولاز بينطلقوا من الفورمولاز اللي شفناهم أنا وياكم. Okay. إحنا شو كتبنا؟ كتبنا إنه في two relations وهول two relations will use them depending on the case. يعني وقت نقول incompressible this means what؟ إنه the volume will not change. V constant. Since V constant, أي equation بنستعمل؟ نستعمل إنه ds is equal to when V constant is equal to شو؟ نحن مش قلنا ds is equal to what؟ Yes. يعني نحن عنا TDS is equal to du plus PdV. Is an incompressible case, what will happen for V? بتروح. Okay, PdV will cancel out. So we can use then إنه TDS is equal to du. Plus, in case the specific internal energy depend only on temperature, هيدا the case of what? The case of an ideal gas. مش نحن بالايديال gas شفنا إنه internal energy will be only function of temperature. And also the enthalpy will be only function of temperature. Please guys, don't confuse cases. يعني نحن ideal gas you only function of temperature. بس إذا أنتوا عندكم مثلا mixture vapor water delta U is not only function of temperature. U will be also a function of the state. يعني أنتوا مثلا إذا أنتوا بقلب الدوم إذا T constant يعني U constant شيء؟ No. لأنه أنتوا هيدا حسب الكواليتي you can get U1 and you can get U2. So you cannot say that always if T is constant U will not change. No, it is valid إذا عندي ideal gas. لأنه for the ideal gas U is only function of temperature. بينما إذا عندي mixture U is not only function of temperature, it's also function of the quality. Okay, so if you have incompressible substance and you can apply the ideal gas law where U is only function of temperature, and you can write then that du is the specific heat C, which is also function of temperature, times dt. ساعتها if you replace du by Ct dt, and since here the only variable is temperature, we can take here temperature to the other side. فبصير عندي إنه ds is equal to Ct dt over the temperature. And to find the variation of entropy, what should I do? I do integral. I do integral from 1 to 2 from this side, and here also integral from T1 to T2. هلا, in case C is function of temperature, we should give you this function. Okay, تقدروا تعملوا integral. أو عادة بالtables هن بيكونوا عاملين الintegral they directly give you the value. هلا we'll discuss this together. Okay, and in case they told you in the problem you can treat C as constant, you can take then C outside of the integral. So شو بتصير ساعتها؟ بتصير C the constant C times integral of 1 over T dt between T1 and T2. وانتوا بتعرفوا انه الانتجرال of 1 over T is ln T2 over T1. Okay, this is why if the specific heat is constant, how we can write the change in entropy? Delta S is equal to C times ln T2 over T1. While if T is variable, we should do the integral. يعني بده يكون معنا C function of temperature. Okay. No.
دكتور عندي سؤال فوق.
No.
قلت لنا قبل شوي إنه إذا كان في change of phase يعني بين 2 points بقلب الدوم بتكون
ما فينا
ال
نستعمل
pressure هي
ساعتها. We
constant.
cannot use this. Okay. لأنه we cannot say then إنه U is only function of temperature. وساعتها ما بنستعمل هول الفورمولاز، شو بنعمل؟ بنستعمل التيبلز. يعني مش نحن هدفنا نجيب دلتا اس، اوكي؟ انت if we have a table thermodynamic tables بنحدد مثلا الكواليتي of point 1 وبنحدد الكواليتي of point 2 وبنقول انه ساعتها فينا نجيب what is S1 and what is S2 from the tables. ما بنستعمل فورمولا مثل هون، مثل ما كنا نعمل قبل. اذا ما كان ideal gas بس يكون عندنا mixture كنا نستعمل فورمولا او نروح على التيبل تنجيب دلتا يو او دلتا اتش.
تيبل.
الا مثلا بالكمبرست ليكويد، بالكمبرست ليكويد شو كنا نقول؟ انه دلتا اتش فينا نكتبها سي بي دلتا تي، اوكي؟ بس بالميكستشر على طول كنا نستعمل التيبلز. وهون اذا ideal gas فينا دغري نستعمل هول الفورمولاز او كمان فينا نستعمل tables. Okay, so for ideal gas عندنا two options, or tables or formulas depending شو بنعرف وشو ما نعرف. Okay, so here in case we have incompressible ideal gas we can say that we can use directly the following formula in case انتبهوا شو الcondition؟ عندنا incompressible و constant C. If C variable we should do the integral. Okay, now same thing in case you have constant now pressure. Okay, تنقول يعني it depend on the configuration that you have. You decide انتو شو بدكم تستعملوا. يعني اوقات هن بالبروبلم بيقولوا لي عندي constant pressure، ساعتها بقول خليني استعمل مثلا ثاني فورمولا. اوكي، هلا اذا بنرجع سوا لهول الايكويشنز هون. For an ideal gas شو قلنا what can we write for an ideal gas? For an ideal gas we can say that U is only function of temperature and H is only function of temperature, and we can write that du is CV dt and dH is CP dt. أيها بنستعمل حسب what we know. يعني for example okay تنقول نحن we don't have incompressible scenario. نحن بنعرف إنه نحن عادة بس يقولوا incompressible يعني this means what? When we say incompressible V constant. Okay, V constant يعني density كمان we consider no variation in volume و no variation in density. ساعتها إذا قالوا لي incompressible model I can use the previous equations. بس إذا قالوا لي ideal gas what is the equation for ideal gas? The equation for ideal gas is PV equal RT. So I have a relation between the variation of pressure and the variation of volume. بس أعرف إنه I have an ideal gas I can use the following relation between P and V. How to use it here? Okay. If we have, let's say, نحن بنعرف إنه we have two relations that we can apply, or we can say DS TDS equals to DU plus PdV. اوكي، انتوا حتشوفوا مثلا في كتير اوقات بالبروبلمز حتى any gas in some conditions we can treat it as incompressible, in other conditions we cannot. كيف بنعرف؟ نحن بنقلكم بس عادة we have what we call a Mach number. الماك number اوكي حسب الفاليو لإله فينا نعرف إذا incompressible assumption will hold or not. Okay, بس نحن عادة we'll tell you treat it as incompressible. If we tell you treat it as incompressible then you can use the previous equation. إذا بنقلكم treat it as ideal gas يعني you can use the following the relations that we'll see now together. Okay, وعلى طول كيف بنجيب هول relations? We always go back to the initial equations. يعني TDS equal DU plus PDV. إذا قالوا لي إنه V constant يعني incompressible I will cancel this term. وبecause it's a gas أخذوا فوق إنه U only function of temperature و H only function of temperature. Okay, هون بطل بدهم يستعملوا ال incompressible assumption لأنه تغيروا الكونديشن. أنتوا بتعرفوا إنه أي متى بيكون ideal gas depending على ال relation بين P و P critical. Okay, so if we are far away from the critical point and Z tends to 1 we can use the ideal gas model. إذا عندي ideal gas بطل أقول إنه